Hey, hello, long time no see, but I'm back with a wonderful video. In this video, what we're going to learn about is an angle bracket when it's loaded in a horizontal direction. What does the free body diagram looks like, and how do you solve the equations of motion for static equilibrium in order to derive all of the loads that are applied to that bracket. All right, so I'm excited to share this video with you. Let's get going. All right, welcome back. So what we're going to discuss in this video is the heel-toe effect on a bracket, except this time the load is not being applied vertically like we have in the other video on my YouTube channel, but this time it's applied horizontally. All right, so first thing we're going to do is take a look at what the bracket looks like. All right, this is again, a simple angle bracket, and the 3D view of this bracket looks something like that. We have this L bracket here. We have two holes which are basically used for screws to fasten this bracket down to something underneath it, some other surface down here, supporting surface, and then we have this vertical leg over here, and then we have a horizontal load. Now I think somebody in the comments asked in the previous video, which had the vertical load, what if we had two holes along this horizontal leg? Now my guess is that what he or she meant was that these holes are like that, because it doesn't really make sense to have two holes like this, okay, because it's not really a good design practice. So this is a very standard design practice to have two holes like that going along the base of this L bracket in that fashion. Okay, now that we know what this angle bracket looks like, let's look at the free body diagram of this bracket and what the loads and reactions look like. All right, so this is the free body diagram. As you can see, we have our px going this way, acting along on the left towards x, negative x if you will, and if you say that this is x and this vertical is y, and the distance or the moment arm of the load px from the base of this bracket is y, and therefore we have this rx going to the right, balancing this horizontal load. Always remember that we must draw a balanced free body diagram. So this balances this load here. Now it's important to remember that this horizontal px would also induce an overturning moment, just like the vertical px did about the axis of the fastener. Okay, but this time it's different. This moment arm is the vertical height of this leg, and it's an overturning moment like this. All right, so that's what that is, and therefore we have a fastener reaction, RFT, acting along the fastener axis, and we also have the heel-toe reaction, which is maximum at the edge of the bracket over here and minimum at the fastener axis. All right, so this is a triangular distribution over here, and approximately 2/3 of the distance of this heel-toe reaction would be where our heel-toe reaction load, that's where it would be acting. So the distance from the fastener axis to that point, 2/3 of this entire distance to the edge, let's assume that as x. Okay, all right, so now we're going to take a look at the hand calculations that we're going to do to figure out what rx is and what rht is and all that good stuff. So what we know here is this is a two-dimensional problem, and we're looking at the cross section of this bracket or the end face of this bracket, and we have three directions that we can use, two directions that we can use for loads. One is along x and the other one is along y, but the moment, we don't have any moments about x or y, but we have a moment about the axis that's coming out of the plane, which is z, mz, okay, which is the overturning moment caused by px. So first let's do the force balance. The first thing we have is px, so sigma fx is equal to 0, right? And therefore what that means is px must equal rx, because there's no other reaction load that can balance this horizontally applied load. There's no other restraint or constraint other than these two fasteners. Now remember that this Rx will be shared among the two fasteners equally. That's the basic assumption here, assuming that this Px is distributed along that edge. Okay, so this is our first solution basically. All right, so next we will use the equilibrium equation Fy, sigma Fy equal to 0. And in this case, what we have are two different forces, RFT and RHT. Okay, so therefore they must be equal to each other. There's no other way, because there's nothing else acting vertically. These two must be equal to each other, and they act as a couple, and we will understand that in the next equation of equilibrium when we do the moment balance. All right, so now we know that there's a moment applied due to Px at the height, or we're using the moment arm y. Therefore what we have is sigma mz acting about the axis coming out of the plane. This is equal to 0, and what we do is we take the moments about the fastener axis, about the fastener center over here, but the axis is coming out of the plane here. Okay, right there. So we take that mz equal to 0, and therefore we have Px times the vertical moment arm y is equal to, because RFT passes through the fastener axis, or the point about which we're taking moments, this moment would be 0. But then we have the heel-toe reaction RHT at a distance of x from this point. Therefore the Px times y has to be equal to RHT, which is the heel-toe reaction, times x, which is trying to counteract this applied moment. All right, so these two moments must be equal to each other. Now we know what Px is, we know y, we know x, and therefore the unknown RHT would be equal to Px times y over x. But then from the previous equation we also know that RHT is nothing but RFT. Therefore RHT equal to Pxy times y, Px times y over x is also equal to RFT. So these are your reaction loads due to the applied moment. All right, and I believe that's about it, guys. This is how you would solve this particular problem when we have a horizontal load. We have a heel-toe reaction, and this is called a balanced free body diagram, and this is how you would derive all of your reaction loads. And it's a simple hand calculation, which is very useful, very commonly used, and we need to learn how to draw a balanced free body diagram as best as we can. Right, everybody makes mistakes, but it takes practice, and the more you practice, the better you get at it. Okay, thanks so much for watching the video. I really appreciate your time, and also remember that if you would like to check out the free blog, which has a ton of free engineering articles on aerospace engineering, especially related to loads and stress engineering and honeycomb sandwich panels and a whole bunch of other stuff, you can visit the free blog at www.stressebook.com/blog. The link is right here, or you could just type that into the browser. And if you want a free e-booklet with some really awesome technical information, you can go to the address here, which is www.stressebook.com/ebook. And you also have some really good paid courses, and that's really the meat of the website, at www.stressebook.com/courses. And as always, I always ask my subscribers and my viewers to subscribe to this channel, like this video, share this video, and the more you share the love, the better it gets for everybody else, and they will thank you for your kind gesture. All right, so thank you guys, and I will see you soon in the next video.